I just started the recording for our July Community of Practice Lead Teacher meeting, and I'm going to turn it over to Ricky to do our check-in so we can see who's here, and then welcome our special guest today, John Bonnell. So Ricky, I'll turn it over to you, and I'm going to put myself on mute.
Okay, so welcome back, everybody. It seems like it's been a long time since the last time we've all been on together. So I just wanted to check in. I know here in the Bay Area, we're like in the depths of our summertime. So I thought a good question would be to ask people how your 4th of July was and how the weather for your summer is going. So for us here in the Bay Area, it's been a pretty typical summer. I live in Walnut Creek, so on one side of the hill, it's 103 degrees, and when I come into work, it's in the low 60s. So crazy weather, but it made for a beautiful 4th of July because we have a great view from the Space Sciences Lab, and I drove in to watch the fireworks, and you could see all the fireworks from all over the Bay, all the way down to San Jose. So it was a good 4th of July for me. Who would like to go next?
Well, up here in Alaska, Petersburg, we've had a summer that we've never had in the 24 years I've been up here. It's actually sunny more days than it's raining. Yesterday, it was unbearably hot. It was almost 75. And don't laugh, but when it gets that hot, it gets hot. And so it's actually miserable. But my biggest concern is we've had a nice summer. We may get a typical winter, which the last typical winter we had about 220 inches of snow. So I'm hoping that we get an open winter, which last year we only got about 30 inches total, which is an open winter for us. So it's been an unusual. The 4th of July was wonderful. It was actually sunny.
Thanks, Vic. So I guess you can just chime in whenever you feel like it, because I don't have a list up, but I'll get one up now.
This is Claire. I can go next. My 4th of July was pretty quiet. I actually spent most of it working, which was unfortunate because the rest, what I should have been doing was playing bagpipes in Novato and going to a big barbecue. But you know, this is things that we do for work, eh? And the weather, I think, if I remember rightly, was pretty nice. I know that the end of my street, it backs out onto the marina area of San Francisco, which is where all the fireworks go from. So that was pretty neat. Of course, the 4th of July is a bonus holiday for me. It's not something that I'm used to celebrating because we don't celebrate at home. So it's kind of like an extra bonus day off. So it's awesome.
I can go, Wendy. My 4th of July was pretty quiet. We stayed at home. We had a little cookout for the family. And as far as the weather, it's hot. It's like 97 and about 70 to 80% humidity. A lot of water in the air, so it's very uncomfortable. So I have the air conditioning on.
I'll go next. It's Jane in St. Louis. My 4th of July was, I guess I could call it interesting. My family shared the stomach flu, and it was a nice 86 degrees on the 4th of July here in St. Louis, which is pretty unique. But this past week, it's been really, really hot, like Wendy was saying, really high temperatures, high humidity, so we've been hanging out inside quite a bit.
This is Dawn. I'll go next. 4th of July was phenomenal. We went to a barbecue, and then we went back home for a little while and just relaxed and and we went to see fireworks. And we went to a suburb of Baltimore. Here there are a lot of suburb communities, and they all have their own fireworks displays. And the fireworks, we were able to get right down in front, and the fireworks looked like they were right over top of us, and it was just amazing. The finale was just, it just kept going and going and going, and then all of a sudden, like, the whole sky turned gold, and then that was it. It was phenomenal. And then, like you guys, like Jane and Wendy, we've been sweltering here in the DC area. It's the heat wave, and the news was talking about how much cooler it's been, but I guess because of the humidity, it hasn't felt cooler to me. And then they said, we're getting ready for our first heat wave. I was like, oh no. So it went up another 10 degrees and another couple notches of humidity. So we're trying to deal with that. I'm looking forward to fall.
Hazy, hot, and humid.
Yeah.
This is Nancy Alley. My husband grew up in Maryland and always talked about the summers being hazy, hot, and humid there.
That pretty much describes it.
So I spent my 4th of July up in Sonoma, which is maybe about an hour from the Bay Area, and it's in the California wine country. Some friends of mine had a house up there, so we got to go to that, and it was very, very nice and relaxing. And the hardest part was coming back home. I wish that I had spent the night over there, but otherwise it was great. Good food, good company.
That sounds wonderful, Nancy.
And it looks like we have Nancy from Texas on the phone. Nancy, can you hear us, and can we hear you?
Yeah, I can hear y'all just fine. Thank you. Yeah, I'm on my cell phone. I'm having some Comcast issues, so there's a technician who's working on things now, so I currently don't have access to Wi-Fi. So, but that's okay. July 4th was great. You know, of course, we did the typical thing of cooking out, and then went to the water's edge over at Kemah to watch the fireworks, and it's always pretty to watch the fireworks over the water. So that's really enjoyable.
So Jim has sent something in the chat. So he's just said great, and that it was hot in northern Nevada. So I don't know if Jim, you don't have access to speakers, but okay. He can't speak, so I'll be his translator. He just says that he had a great 4th of July and that it was hot in Nevada.
No, it was hot in Nevada.
Oh, there you go. Okay.
I'll be very quick and to the point. Great and hot. Okay.
So who haven't we heard from yet?
This is Karen. Can you hear me? I have a new microphone. Okay, thanks. I had an awesome 4th of July because it was the reunification of 3 best girlfriends, and we got together in Aptos, which is a small town near Santa Cruz, California, and we went to the small town parade, and we cheered everybody. We were standing on the back of an open bed truck, and we cheered everyone, including people who weren't in the parade. So we'd say, like, yay, guy with yellow sneakers, yay, teenager with dog, and, you know, gave everybody a little boost. It was fun.
I lived in Aptos when I lived in Santa Cruz.
No way. It's a cool town.
John, how was your 4th of July?
It was good. We ended up with folks at our house cooking barbecue, and then got everybody up on the roof. We live down in the flats in Berkeley, and so we really couldn't see all that much except for the fireworks show down at the Berkeley Marina. But it was nice. Just kept, like, it seems like things just go on longer and longer. That, you know, when you're a kid, they go on for a long time, and then when you get to be a teenager, it's like, oh, it's done too quick. And now maybe they're just like spending more money on it. Anyway, it was wonderful.
So is there anyone who hasn't got a chance to us know?
Renee is here. Can you hear me? I think my mic's on. I'm here. Okay. I'm also in the Bay Area, so you've heard a lot about our weather. I went to a family barbecue for 4th of July. That was nice. And then, like John, I was able to watch at least the Berkeley fireworks from my house. And that was really nice. So it was very low key.
So I think that's, well, did we hit everyone who's on right now? I think so.
No.
You did.
I am.
Yeah.
We have had a lot more rain than usual, which we're happy about. It has really helped us this year. So between thunder showers, we grilled, and then they shut off fireworks. And there's our town, the next town over, and then every condominium on the beach feels like they should shoot them off too. So we are surrounded by fireworks in every direction. So that was it for us.
So that just reminds me, July 4th is actually my anniversary of when I moved to the Bay Area. It was 3 years ago on July 4th that I flew in. I was living in Hawaii before that, and my flight landed right. It was coming in right as all of the fireworks were going off. So we were coming into land into Oakland, and we could see the San Francisco fireworks going off. We could see the Berkeley fireworks going off. We could see the Oakland fireworks going off. We could see the San Jose fireworks going off. And then all of the neighborhoods that had fireworks going off. It was just like everything was going off all at once right as the plane was landing. And it was a perfect...
That's because you were coming.
Yeah, that's what I thought. It was a great entrance, a great welcome to the Bay Area, that's for sure. So I think let's move on to the next part of our agenda. Thanks, Ricky, for getting us started. And today we have a guest speaker, a guest scientist, Dr. John Bonnell. So I'm just going to read you a little introduction about him, and then John, I'll turn it over to you for your presentation about the Van Allen probes mission. So John Bonnell did his undergraduate work in physics here at UC Berkeley. He started working at the Space Sciences Lab as an undergrad, hanging magnetic tapes and writing C code for data analysis for Dr. Cynthia Cattell. And I have to say, when I first read that, I got this image in my head of like taking audio tapes, and you know how you pull them out and hanging them around, which I'm sure is probably not what you were doing. But that's the image that came forward.
No, not those bigger tapes.
So after graduating, John worked for 2 years at SSL as a programmer and researcher before starting a PhD program in space plasma physics in the Electrical Engineering Department of Cornell University under Dr. Paul Kinter. Upon completion of his PhD and follow-up postdoc at Cornell, John took a 2-year postdoc with the Space and Atmospheric Physics Group at Los Alamos National Laboratory. He returned to SSL in the fall of 1999 and began working there ever since. He currently splits his time between a modest amount of scientific data analysis and a lot of time spent on electromagnetic field measurement hardware for satellites and rockets. And I would just like to add to that John has been very supportive of education public outreach, which has been great. And it's been a pleasure to work with him. And I've already learned a lot about the Van Allen probes and related science. So I'm very pleased that he's here today and is taking time out of his schedule to join us.
Oh, thank you, Nancy. I'll see if I can live up to that beginning. So, you know, having not spoken to y'all before, I'll apologize in advance if I've not quite calibrated the level of my talk, but we'll see where we go. And if you have questions as I go along or afterwards, I'll be happy to expand and go over other things. I'm going to go ahead and try sharing my screen. All righty. We're going to go ahead and put this up for full screen. Can folks see from edge to edge of this?
So what I can see is to it does start to cut off. So I think we might need to try it the other way.
Okay. It also could minimize the screen of participants. That's covering up a fairly good share of mine.
All righty. How's that?
The green minus arrow will take care of your screen.
Okay. All right, let's see what this looks like. All right. What's this look like to you, Nancy?
Yeah, that looks good. It looks like we can see I can see part of your desktop background, which is taking up some room. So there we go. That's better.
You like that?
That's better.
Okay.
Let's try.
I want to try it. Okay, so, but if I do this, you can't see the whole width?
That's right.
Okay.
I can't see the whole width that way either.
Okay.
I've got a huge gray spot on my left.
Like over on this side?
Yes, that's the size. I got, you know, about a third of my screen is now.
There's a big gray spot over there.
Yes.
Okay.
And now I can see underneath. I can see your there you go. Thank you.
How's that?
That's great.
I can see the whole thing now.
Do we have consensus on viewing?
I can see it really well now.
Yeah, it looks good to me.
Excellent. All right. Well, I just want to thank Nancy and you all for inviting me to come to your meeting and give a talk about the Van Allen probe's mission. You know, let's see, we launched in September, so we're about 9 months into the first year of the mission. And I'm going to talk, just give you a brief discussion because I'm not sure how many of you have been exposed to what parts of the mission. So I'm going to talk a little bit about our schedule and the launch, you know, essentially how did we get to where we are now. And then the mission design, which is where have we gone in the Earth's magnetosphere, where will we go in the future, and also talk about the instruments and the data products that we're producing with the Van Allen probes. And essentially that's what do we measure and why are we measuring it. Then I'll spend some time and talk about some of the interesting campaigns and observations to date. Some of you may have heard about one of the early results that went out in Science by Dan Baker and others about the so-called third belt that he discovered or observed in very early in the Van Allen probe's mission, and also just the general variability that we're seeing. And also I'll touch briefly on a joint campaign between Van Allen probes and the barrel balloon campaign that went in Antarctica in this past January and February. Just to give you an idea of the mission, this is actually a slide I put together for my team. I work for the Electric Field and Waves instrument. It's one of the two teams that does the electromagnetic field measurements on the Van Allen probes. We're mostly responsible for the electric field apparatus. The other team is responsible for the two sets of instruments that measure magnetic fields on the spacecraft. and we have a division of labor and frequency space, which I'll show you in another slide. But this is just to give an idea of sort of the level of effort that went into what we were working on. We actually started proposing to this mission back in 2005. We were selected in 2006. We launched in 2012. So we spent about 6 years doing the design, fabrication, assembly, test of these instruments and the spacecraft. And just between when we finished up our instrument builds and when we did launch, we basically, on our team, expended about 200 person-years of effort on this. And so you multiply that by the 5 instruments plus the spacecraft, and you've got about a millennia year, or a millennia person year, or a person millennia, or something like that, of effort that's gone into putting these 2 probes into orbit around the Earth. Once we did the launch on August 30th of last year, we spent about 2 months bringing the instruments online, and then started up normal operations in 2012. We're in the midst of that right now, and I'll show you some stuff about the orbits and where we are. The end of our nominal mission will be in June or July of 2014. We, of course, hope to get extended mission, and we have the resources to do that, basically out to about 2016. So you may or may not have been at the launch. Just to show you a couple of nice pictures. This one here that I'm emphasizing here. This is actually the 2 Van Allen probes stacked, one on top of each other, A and B, with their solar panels folded down in the stowed configuration around them. Inside, essentially the payload cover or fairing that's going to go up on top of the Atlas V rocket that was used to put these vehicles in orbit. Try not to move that around. This is actually a nice picture of the launch. Again, we launched on the 30th of August at about 4 o'clock in the morning, Eastern Daylight Time. We did it from one of the pads there at Cape Canaveral Air Force Station. Those of you, it's Cape Canaveral or Cape Kennedy, depending on what area you grew up in. Just to give you a sense of scale of these spacecraft, here you can see about half of a technician who's working on the underside of one of the probes, and then this whole stack goes into this cover here at the top of the rocket. This all goes up into space. And then this is an artist's conception of the 2 vehicles on orbit. Very soon after they've gotten onto orbit, this is a few hours after launch, we've opened up the solar panels, put out the booms that get the magnetic field instruments away from the body of the spacecraft. And the 2 spacecraft are separated by, I think here they appear to be rather close. I think in actuality they were several kilometers apart at this point in the mission, basically to reduce the probability that they would bump into each other, which would be a bad thing. So once we got these vehicles on orbit, with the Atlas V, what were we trying to do? So just a simple cartoon. It sort of shows the basic orbit geometry. You've got the sun over here, you've got the Earth here, and then you've got the 2 Van Allen probe satellites sharing almost identical orbits. They're highly eccentric orbits around the Earth. They come in within about 600 kilometers altitude during closest approach, and they're out at, unfortunately I'm mixing my units here, they're out at about, I think 32,000 kilometers at their furthest distance from the Earth. Now, the way that the orbits are set up, the period is about 9 hours, although one of the 2 vehicles has a slightly shorter orbital period. It moves faster in its orbit than the other. What that does is, over time, as we go through the mission, this, as the 2 satellites orbit around the Earth, one goes faster than the other, and it slowly works its way ahead. And it'll basically come around and, over the course of time, lap the other one in about 70 days. So part of the reason why we're doing this is that we're interested in studying what's going on out in the magnetosphere at both close approach, small distances between these two vehicles, so on the order of a few hundred to 1,000 kilometers, to much larger differences, essentially all the way across, from one side of the Earth to the other. And what that does is it gives us a way of looking at how disturbances propagate through the system in space and time at a lot of different distances. And just through orbital mechanics, by setting these two vehicles up with slightly different orbital periods, we basically get all of those separations over time for free. Now, the other thing that happens with these orbits is that, if the Earth was a perfect sphere and we didn't have the gravitational perturbations from the sun and the moon, then these orbits would they'd stay in a nice ellipse, and they'd stay fixed in inertial space. But because of the equatorial and the southern hemisphere bulge of the Earth, as well as small gravitational perturbations from the sun and the moon, the actual ellipse of the orbit slowly moves in its orbital plane, and the orbital plane itself actually rotates around a fixed direction in space. And the sum of those two things is that basically the line going from the perigee to the apogee, the line of apsides or apsides, depending on how you want to pronounce it, that rotates around at about 220 degrees per year. So essentially we take our line of perigee and apogee all the way around in local time relative to the sun in about 1 year and 8 months. And again, this is a really useful and important thing. We're not using any propulsion to do this. We're just relying upon natural perturbations to the orbit from the fact that the Earth's out around and the sun and the moon are around, in order to take us and scan us through a lot of different regions around the Earth. And it turns out that the night side of the magnetosphere is different than the day side. The dawn side is different than the dusk side. And so this is really important for us to really understand what's going on all the way around through all the local time. So there's a few other things on here that I've included. The orbits themselves are at a fairly low inclination to the Earth's equator. What this does is it allows them to do a really good job of sampling the region close to the magnetic equator, which is offset from the terrestrial equator, the normal equator of the Earth, by about 10 degrees. And that wobbles up and down because the magnetic pole of the Earth is off center from the spin axis of the Earth. But it keeps us in a very interesting region of the magnetosphere, again, a region where you've got a lot of electromagnetic wave activity. You have a lot of energetic particles that don't leave that region. And if you don't target that low inclination with your vehicle, you don't get to see basically where the action's happening. The penalty that you pay is when you launch out of a place like Cape Canaveral, you naturally will go into an orbit that's about 27 degrees of inclination. And so you have to pay a penalty in terms of how much satellite mass you're going to put on orbit in order to shift your orbit down to this lower inclination. Now, for us, the Atlas V that we got for this launch had plenty of launch capacity. It really was not an issue. But there's plenty of other missions where it definitely is something that you have to think about, and it's a trade in terms of how you design your mission, in terms of where you want to put your observing vehicles, and how much money and effort you're going to spend on your rocket to get there. So if we think about where these orbits sit in kind of your standard belt picture of the radiation belts and the Earth's magnetosphere. So first I'm going to show you a graphic that was put together that shows where the two vehicles are relative to this two belt system that has been the standard way of depicting as well as thinking about the Earth's radiation belts since Van Allen discovered them in the late 50s. And what you can see is that we start out well outside this broad outer belt where you see the strongest fluxes of the millions of electron volt relativistic electrons. And then we plunge deeply into very close to the Earth through this inner belt that's dominated actually by much higher energy protons in the billions of electron volt range, that come from actually cosmic rays impacting the upper atmosphere of the Earth, producing neutrons, and those neutrons decaying into high-energy protons and electrons. Also, some of these electrons are ones that have survived this so-called slot region. This is a region where there are strong processes that scatter particles out of this essentially magnetic bottle that contains them out here. As they move in, they get scattered, they get lost in the atmosphere, but a certain amount of them are preserved, and then there's also some that are generated in situ. But what you see is that we basically go from the low Earth orbit, where you have various sorts of satellites like the Iridium satellites that are used for satellite communication. Basically all of your military or a lot of your military surveillance and communication satellites sit in low Earth orbit. And then we go almost all the way out to, we go through the orbit where the GPS satellites sit at about 4.4 RE. And then almost all the way out to geosynchronous. Geosynchronous is at about 6.6 RE, and we only go out to 5.8. But basically, we traverse one of the most dangerous regions in the terrestrial magnetosphere on a regular basis and on purpose in order to characterize it. So, again, to sort of situate this in a little bit bigger picture of the Earth's magnetic field, or the structure that's formed by the Earth's magnetic field in response to the flow of the solar wind and the solar magnetic field that flows with it. Again, you've got the Earth down here at the center. You've got this outer radiation belt here. You've got embedded in this a region of lower energy positive ions called the ring current that circulates. Typically it's protons and oxygen, and this actually has a significant effect. The electric current carried by the circulating particles in this ring current has a significant effect on the structure of the Earth's magnetic field. It essentially inflates it out, and depending on how quickly or slowly it inflates it out, it can just move the relativistic particles with it, and then they come back in as the ring current dies away. Or if it's enhanced very rapidly, it can shock them and contribute to either scattering or acceleration of them. And so we have instrumentation on board that is built to measure the ring current particles and understand how that fits in with the magnetic field measurements we're making both in space and on the ground. Surrounding the region that's dominated by the Earth's magnetic field is a boundary layer. It's called the magnetopause. And this magnetopause is essentially a layer of electric current, and it serves to separate the flow and magnetic field of the solar wind flowing over it from the Earth's magnetic field inside. So there's much less particle flow from the solar wind into the magnetosphere than there would be if there wasn't a magnetopause there. And it's actually a form of a shock wave. But one of the things that can happen, and I'm not sure if we've actually seen this happen yet on this mission, is sudden changes in the flow speed or the direction of the magnetic field can essentially compress this outer boundary and really send electromagnetic waves in, compress the particles, just like when you compress a balloon full of gas, if you do it quickly enough, you heat it up, and that's something that happens in response to passages of different shocks. So again, we're starting out close into the Earth. We go out to the edge here. We're down in this equatorial region looking at all sorts of different electromagnetic phenomena that are happening and various sorts of particle drifts that are happening that are carrying the particles around, exposing them to different kinds of electromagnetic waves and resulting either in their acceleration or their scattering. So that's a lot to hit, but once we're there, and you got to believe me, it took us, I think, 9 months to come up with these 3 bullet points. It was excruciating. But once we're there, what are we supposed to do? And, we're supposed to provide an understanding, ideally to the point of predictability, of how the populations of relativistic electrons in that outer radiation belt and the penetrating ions that we can see in other places, how does that form or change in response to what the sun does to the terrestrial magnetosphere. And we boiled that down to what physical processes enhance the radiation belt, what are the processes that take electrons out of the belt, and how does the ring current and other geomagnetic processes affect the radiation belt behavior. Now, the instrument package that we took out there was a collection of instruments for measuring essentially the number of charged particles in a particular energy range of a particular sign or mass or species, coming from various directions out in space. And so we're measuring electrons, we're measuring protons, and then we also have instruments that can measure the mix of protons, heliums. Okay, so we got a question from Jim. What's the protocol for answering questions? Do I do that as we go, or should I save them up?
It's really up to you. If you want to wait until the end to take questions, that's fine, and I can keep track of questions that came in through chat also. Or if you want to just stop and people can jump in as you're going through, that's fine too. So let us know what you prefer.
Sure. Well, yeah. So I see on the chat, James is asking how much of the electron masses change due to relativistic effects at an MEV, and unfortunately, I haven't used my special relativity in quite a while, so I don't know exactly how much the mass has changed. But I believe, so the equivalent, the energy equivalent of the mass of the electron is about half an MeV, and so that basically sets the dividing line for non-relativistic versus relativistic. And I think, if I remember correctly, if we're up at an MeV or so, you're probably looking at an effective mass about twice that of the original electron mass. I can certainly fix that, but you're not dealing with with several orders of magnitude. It's more sort of orders, less than an order of magnitude of change. So, but I think one of the things that really sort of struck me about this mission compared to other missions that I've worked on is just the range in energy that we go from. We're basically going from 1 eV, which is sort of what we call the thermal plasma. That's the plasma that's carrying the bulk of the density. It's the coolest plasma that's present. This 1 eV, this means that it's about, compared to room temperature measured on an EV scale is about 1/40th of an EV. So it's quite a hot gas to begin with. It's very tenuous, and so it's not like we have to worry about heat conduction from this gas of charged particles to our instruments. But just to sort of give you an idea of the temperature. But we go from 1 EV with some of these instruments. HOPE, for example, HOPE measures electrons, protons, and then also the mix of hydrogen or protons, helium, and oxygen, which are the dominant. That's the dominant components of the positive ion population out in the magnetosphere. And it measures those from about 1 eV up to about 30 kilovolts. We then, other instruments sort of pick up the place here. This mag ice makes measurements of electrons and protons, starting in that tens of keV range and goes out to a few MeV. So it starts to look at, in the electrons, the relativistic population, as well as the top edge of this thermal population, and then a super thermal piece. RB Spice makes measurements, again, in this sort of intermediate range, but it's designed really to be looking at the ring current ion population. So protons and oxygen in this few tens of keV up to a few MeV range. Finally, you get into the really relativistic particles with REPT, and it starts at a few MeV and goes up to tens of MeV, or even hundreds of MeV protons. And then finally, there's the fifth instrument is RPS, and RPS is built especially to look at the really high energy protons that live in that inner belt. And it starts at a few tens of MeV and goes up into the GeV, the billions of electron volts. And I used to tease them because the first time I saw a picture of their instrument, I don't think I could see an aperture for the particles to go through. And truth is, they don't need one because the particles really don't notice that the spacecraft is there. And the way that they define the aperture of their instrument, both RPS as well as REPT, to a great extent, even down into the range where MagIce and RB Spice are making their measurements, they really have to look at how many particles are coming from a particular direction in space, but at the same time, they have to look at what particles are coming from other directions in space and kind of do a coincidence, anti-coincidence thing, because there's no way that they could carry enough shielding around their detector to define it just in terms of an aperture. And so, you know, RPS, for example, I believe it's got 12 silicon detectors stacked up, and then another tube, and then basically a scintillation tube in the back. And what it does is it looks for a whole series of those dozen silicon detectors to go off in the right order with the right signals on them in order to say, yes, we had a particle come from that direction in space. So what was that? Yay, I was hoping to get a copy of that. What's that question? I'm not sure what that is. Oh, maybe it was.
Sorry, I was trying to send that to one person and it went to everybody. My fault.
Oh, no problem. That's okay. Okay, so just, so anyway, that's in terms of particle measurements, that's what we're doing there. In terms of the electromagnetic field, you know, we want to measure both the magnetic and the electric parts of it. We had a wonderful shotgun marriage with the folks from University of Iowa in terms of how we decided to divide this up. We both had proposed full suites of electromagnetic instruments, and NASA, in its infinite wisdom, divided it up between the two of us. But we've turned out to make gold out of straw in a lot of ways. We make lots of measurements of the electric field at low frequencies, as well as all the way out to about 500 kilohertz. And these different frequency regimes correspond to a lot of different kinds of waves. You know, some of these down at the lowest frequencies are just the electric fields and magnetic fields that push the particles around as they're moving around in the magnetosphere. As you get up into this kilohertz band, into the tens of kilohertz, those are actually waves that can be, I love this, gold from colliding neutron stars. I think I saw that on Slashdot yesterday too. Okay, so those are the waves that give you energization of the relativistic electrons, as well as scattering of the electrons and loss into the Earth's atmosphere. And then finally, you get up into these higher frequency bands, and really what you're looking at there are waves that help us diagnose what the density and magnetic field is out in the plasma, and they're more of like tracers for what's going on elsewhere out in the solar wind or locally around the vehicle. Again, we're covering a large range in frequency, and we're covering a large range in amplitudes with the fields measurements. So let's see, we're doing a lot of time here. So let me just get into some of the measurements here. And I'm going to jump right in with this plot of the relativistic electron fluxes. And this plot, I'm going to go into this in some detail so that you guys get a feel for what you're looking at. This starts back on September 1, and this is data that was provided by Dan Baker's group at LASP. It's data from the REPT instrument, and one of his grad students, Allison Janes, provided it to me via Mary Hudson. We start here in September of last year. We go all the way out to May of this year. And what you've got is in different, okay, what holds the belt together and does Van Allen change shape? Okay, so what holds the belt together, basically why the belts circulate, is it really has to do with the Earth's magnetic field. So when you have a charged particle in a magnetic field, what it wants to do is it wants to circulate around that magnetic field. the magnetic field direction. If there is a, and then if you think about the Earth's magnetic field, it, as you move away from the Earth, the magnetic field strength goes from very strong at the surface of the Earth to much weaker. It falls off, essentially with an R cubed fall off. Okay, what that does is it changes the radius of curvature of that orbit of the particle around the magnetic field line. And when the magnetic field strength is strong, the radius of curvature is small, and so it's a very tight turn. And then when it goes out further away from the Earth, the radius of curvature is bigger. And so you essentially end up with this neat sort of cycloid motion. So this, and I'll try and do this in front of the thing. Essentially, the particles do this around the Earth. Kind of like, those of you who are old enough, you may remember a spirograph or something similar. But essentially, you've got this lovely cycloidal motion of the particles around the Earth. So, and so that, in essence, is what holds is what gives the belts their belted shape. Once you put a particle in there, it's going to circulate around. Now, the question is, how do you put the particle in there in the first place? And that's something that, that we're trying to discover with this mission, and, that other missions before. Does that answer your question, Vic? Yes. Okay, excellent. All right, so going back to the plot, what you've got is you've got a variable here that's marked as L star, and I'll tell you what that means in a second. But essentially, you can think of it as distance from the Earth, so radial distance away from the Earth. So we start at 1, so we're at the surface. We go all the way out to 6, so that's when we're out at apogee, we're 6 Earth radii away from the from the center of the Earth. Each of these panels is one energy channel from the repped instrument. We start here at 2.3 MeV. We go up to about 3, 4.5, 5.5, 7, almost 9. And what's shown in color is the flux, the number per unit area, per unit time of particles, in this case electrons, integrated over all of the look directions from the instrument and over time. So, and it's done in a color bar where the cool colors, the blues down at the bottom, are the small fluxes, so, and you're basically seeing about a factor of 100,000 change in the flux as you go from the bottom of the color bar at blue up to the top of the color bar at red. And so what you can see in here, and I'm going to do this, I think I'll do it with this 4.5 MeV channel because that's the one that we're going to zoom in on, and we're going to talk about this third belt idea in the next slide. Nominally, if you sort of look at a particular time here, and you come in from the outermost distance all the way through towards the center of the Earth, what you see is, maybe I'll do it over here where the outer belt's not quite so broad. You come in, and there's a region where the fluxes are high, and then you drop down, here in this low flux region, and then you pop back up, and then you're back at you're at the surface of the Earth, and so there's no more flux. And this is essentially, as your satellite goes out to apogee and back in, out and back in, you go from the inner belt electrons through the slot region, where the fluxes are quite low, through the outer belt region where the fluxes are high again, back in, out and in. Now, what you'll see here in this early region, and this is the thing that was so exciting to the team and to Dan, is you had the inner belt, you had this outer belt that had been generated by this, whatever this event was here, very early in the mission. But then you've got a third belt stacked up out here outside of the other two. And so the question was, how did that happen? What led to the separation between these two outer belts? And so, and sort of understanding how that happened is still in process, but just the observation of it, this was the first time that we had such a clean, clear signature of it going on. There had been hints of this at lower energies with less resolution, with a lot higher backgrounds in the instruments that just made it so that it was not nearly as clean and definitive. And really, part of the design of both the electromagnetic field measurements and the particle measurements on this instrument was to clean things up and make it so that we could make really clean observations like this and really, make clear conclusions about what's going on. Now, the tricky thing about this plot is this L star. I said that it's basically the radius away, or a radial distance away from the Earth. Now, there's some adjustments that are made to that have to do with essentially what I mentioned earlier about how this ring current can make the Earth's magnetic field sort of breathe in and out. Now, if it does that slowly enough, this idea that you've got these cycloidal particle motions going around the Earth, and as long as you change the magnetic field slowly so that basically those particles make a lot of those drift orbits by the time you've changed the magnetic field strength significantly, basically the particles will breathe out as you're sort of inflating the inner magnetosphere, and they'll breathe back in if you do it slowly enough. And what this L star is supposed to be doing is it's supposed to be taking out that, there's a term for this, it's called adiabatic motion. You're basically doing things so slowly that the particles stay on the same trajectory, stay in the same state as you change this parameter slowly. Now, what you're seeing, though, is that over time, there's this general trend of the high flux region to slowly migrate its way inward. In addition to that slow migration, you also have these step-like changes. So here, we have this step-like change where we've all of a sudden injected this outer belt. We have a step-like change here where we've injected this second outer belt, and then it's diffusing in. Here, we have a big injection, probably at I think this was a geomagnetic storm, or it might have been a shock passage, where we dumped in a whole lot of flux of energetic electrons, and that persisted for a while, and then another storm came along and just cut it right off, cut off whatever was going on, whatever flux was circulating out here at this distance, just got carved away, and it's like it wasn't there at all. I think that's one of the more interesting things. This is, for me, this is an effect that happens when that outer boundary, the magnetopause, comes in, and essentially the particles that are drifting around out far enough away from the Earth, they hit that magnetopause, they scatter out, and they are lost. And then when the solar wind lets up and it expands away, all of a sudden you've carved off a big slice of your outer belt. Now, this sort of slow variation in time, that's believed to come from, it's essentially a diffusive process. And what's happening as the particles traverse their drift orbits, they're always being jiggled by small amplitude electromagnetic fluctuations. And essentially that jiggling, it's sort of like a Brownian motion, and it slowly causes them to diffuse inward. Now, there may also be some systematic effects in how this L star is getting calculated. You have to do it with a model that you can put inputs from your solar wind satellites or your RBSP or Themis or other satellites that are buried in the magnetosphere. But there may be some systematic stuff that's going on. But just to sort of focus in on this short period, or not too short of a period, about a month-long period, there's a lot of stuff going on in this plot, and I'll talk about it just briefly. Again, this is a panel. This is the 4.5 MeV electrons. Again, this is radius. And this picket fencing that you can see, this is actually, what you're seeing here is that as the spacecraft goes out along one longitude and back in along another, it's seeing slightly different parts of the radiation belts. And so you're picking up this variation in local time or variation in longitude around the orbit of the fluxes. And so it's very repeatable. But what you can see here is this outer radiation belt that's been injected, forms sort of a normal outer belt here. And then, in Baker's terminology, this is what he called the storage ring, which is a remnant of the previous outer belt. Then there's another injection that piles these guys in on top of it. And then something happens that cuts out both of the outer belts. And then there's another injection event that energizes and puts particles into the outer belt again. Now, these lines that are down below, there's a couple of panels. This panel and this panel show the solar wind speed and also the magnetic field strength and direction in the solar wind. And both of those things, so why is Dan Baker showing these quantities against what's going on in the radiation belt? Well, what the solar wind speed and magnetic field does is it acts very much like a generator, and it serves as a way to drive the flows of plasma inside the Earth's magnetic field. And so you can oftentimes see various sorts of correlations between the solar wind speed and the magnetic field. Now, the exact causal relationships between those are not well understood. And again, that's one of the goals of the mission, is to understand if we see certain changes out in the solar wind, an hour or two upstream from us, are we going to see a big geomagnetic storm and a big change in the radiation belts? And right now, we don't know the answer to that. And by the end of the mission, we hope to have an answer to that. This other panel down at the bottom, this so-called DST index, this is actually a measurement of the magnetic perturbation from the ring current. And again, it's a measure of this inflation and deflation of the magnetic field down close to the Earth. And you can see that there's definitely some correlation between here, the ring current strengthening. Here you can see the outer belt getting sliced off. Again, this abrupt increase in the ring current and an inflation of the inner magnetosphere corresponding to the outer belt getting carved off. Same thing here, but you recover and you get this flux back. So there's a lot of different stuff going on here. But again, the really exciting thing about this was being able to see these features in the relativistic electrons so cleanly and so clearly for the first time. So just to close out, I want to talk briefly about this barrel campaign. This was another mission. It was set up. It's a multiple balloon payloads that were launched in Antarctica. They each carried balloon-borne X-ray detectors at about 30 kilometers altitude. And as is sort of shown diagrammatically, you have these energetic electrons that are coming in along the Earth's magnetic field, and those energetic electrons hit the neutral atmosphere and produce X-rays in a characteristic spectrum that then get measured by the detectors on the balloons, and then allow you to go back and look at, essentially determine what the spectrum of electrons that was coming down. So again, what you're looking for here is the causes of electrons being lost via precipitation. We talk about precipitation in space physics the same way you talk about precipitation in meteorology. You're allowing, just like in meteorology, you have water coming down out of the clouds, and that's called precipitation. In magnetospheric physics, when we have energetic ions or electrons coming down out of the magnetosphere and hitting the upper atmosphere, we call that precipitation. And this is a loss mechanism for the radiation belt particles, as well as other particle populations out there. Now, I wasn't really quite sure what to show you guys all the different stuff that was going on. I mean, this was a fascinating and it was a fascinating campaign from just a social point of view, because we had there were two teams, one from Dartmouth, one from Berkeley, that were stationed here in Antarctica at Sinai and Halley Bay, that were doing the balloon launches. We had a group at Santa Cruz. We had a group at Dartmouth. We had a group up at University of Minnesota from our team, as well at University of Iowa and other of the instrument teams that were collaborating on a day-by-day basis as they launched their balloons, and we sort of watched where the magnetic foot point of the two Van Allen probe satellites were going to sit over the Antarctic continent. And when they observed increases in their, we basically would lay a trap. We would say, okay, balloon 1G is going to be close to the foot point from RBSP-A or RBSP-B at some particular time of the day. We would set things up so that we were doing high rate data collection at that time. And then if, in this case, this is, I think, I can't remember if this event is late in January or in mid-February, from the balloon detectors, if they saw spikes in their X-ray fluxes, we could then tell our instruments on board to download high rate data about the electromagnetic field, both from the EFW instrument as well as the emphasis instrument. The particle instruments could provide data about the electron distributions as well as the ion distributions. And we could start to put a picture together about what the magnetosphere was doing when you got these, either longer duration X-ray bursts or shorter duration X-ray bursts. And this is very much a piece of work that's in process and that has a lot of really great young scientists and postdocs and graduate students working on it. And again, like I said, it was this wonderfully social experiment, I want to say, but also experience, sort of doing this globe-girdling collaboration via the phone every day, and to sort of put this together and really try to understand how these processes work. Now, I've gone way longer than I expected. I'm going to close up here, but essentially, I just want to let you guys know there's more to come. Our primary mission should continue through October 2014. That precession of the orbit that I mentioned earlier in the talk is going to sweep us. It's already swept us through the night side, and we've seen just amazing sorts of stuff. Not only the relativistic stuff that we saw, but all sorts of interesting charging events and things going, particle injections that are going on. And then as we sweep around through the dusk side and over into the day side magnetosphere, we're going to start to see what are called plumes, which are high density plasma that's carved off of a completely different region that I didn't get a chance to tell you about, in closer to the Earth. And we'll see those and their effects on what goes on with the other particle populations. We'll see all sorts of low frequency waves, these electromagnetic ion cyclotron waves. We'll probably, depending on the strength of the solar wind, we may actually encounter the magnetopause on the day side, and that would be exciting. We'll see lots of differences. And as I mentioned before, we basically have enough fuel on board. We need fuel on board not to sort of keep us up in orbit, but to keep us pointed at the sun. Our solar arrays only point in one direction, and we have to keep ourselves pointed roughly in the direction of the sun, and that's what consumes most of our fuel. And we've got enough to run basically through 2016 if and when NASA gives us an extended mission. So we've got a lot of stuff lined up for the rest of the regular mission, as well as stuff to look for in the future. And then there's just some other stuff that I put in here. I figure I'll give this to Nancy, and you guys can have a copy of it as a PDF, and then if you're interested in looking further at stuff, we can go from there. But I'm going to go ahead and I don't know whether I should keep sharing, Nancy, if people want to go back and ask questions, or do you want me to unshare, and how do you want to handle the next transition?
Sure. So first of all, I'll say that if it's possible to, John, for me to either put the PowerPoint as is, or I could turn it into a PDF and then upload it to Wigio, which is our online discussion board. If that's acceptable to you, John, then I can do that so that the teachers have access to it.
I'll be glad to do that. I'll email it to you when we get done today.
Great, thank you.
And nothing in here is sensitive, and so it's all good.
Great, thank you. And then I know we've gone a little bit over time, but I see that there's some questions, so I want to honor that. So please keep sharing your screen. And
okay.
Jim had a question. Are you able to or have the ability to detect muon showers?
You know, it's interesting. That's actually how the guys with the GeV particle detector, that's how they did some of their calibration work on the ground. Because basically, I think they have to go to a particle accelerator to do their calibration. But then what they could do to test the functionality of their instrument is they would just set it up and have it running, and you could detect the energetic particles from muon showers with that thing. So RPS can do it. I mean, I think that if I remember correctly, like muon showers, that's more sort of like cosmic ray stuff that happens. You sort of have to have the cosmic ray interact with the Earth's upper atmosphere first and basically shower out the muons from that, if I remember correctly. But, essentially they can make measurements up in there, and I think that that's a background issue for them. Does that answer your question? Excellent.
John, I've got a question. And first of all, I'd like to just ask you a simple, if I'm reading this correctly. And that is, so therefore the Van Allen belt is the result of the interaction between the Earth's magnetic field and the various sources of plasma that's running through our solar system.
That's right. That's exactly right.
Okay, then what really happens if we get one of the more, shall we say, severe CMEs, some of the past history ones that actually get pointed towards the Earth, which have a major, major effect on our magnetic field?
Yep. Yeah, so it's tricky. So there's two things that happen. I mean, if you get a major CME that comes in and it's got the right polarity of the magnetic fields, essentially if the polarity matches the polarity at the front side of the Earth, really all it does is it compresses. If it's reverse, it can actually couple in and drive a whole lot of other interesting stuff that happens. But essentially what happens is you peel back or compress that magnetopause. And initially what that would do is it's going to strip out that outer belt. But because you're doing this compression, any particles that are back in the Earth's magnetic tail, you're providing a way of energizing those so that then when you relax, those energetic particles then can come in and repopulate the belt. Yeah, exactly. CME BZ field south directed. That's what I was talking about in terms of like the most G-effective CME. So you you get an initial dropout in the flux, but then it would probably come back with a vengeance because you pumped so much energy into the system and then sort of re-expanded the Earth's magnetic field to allow for the containment. Does that make sense?
Yes, and then I want to go one step further, and when the magnetosphere on the shadow side reconnects, it basically drives plasma into the Van Allen belt.
That's right. So that's one of the things that we can see, and it actually, I mean, unfortunately, I didn't have any good plots to sort of show those kind of injection events. But as we were sweeping the apogee of the orbits through that midnight sector, we saw multiple instances where you could see lower energy electrons, sort of tens to hundreds of keV, being pushed in from the tail in response to the enhanced reconnection. And so, the thought is that sort of forms a seed population, and then you have processes that are going on closer into the Earth that actually take them up, from the tens to hundreds of keV into the MeV range. And some of those are resonant processes with high frequency waves, where basically you're resonant with the gyro motion of the particle around the magnetic field line. And some of them are actually resonant processes with much lower frequency waves, where essentially you're resonant with the drift motion of the particle around the Earth. Does that make sense?
Yeah, thank you.
Okay, cool. So yeah, and then Jim asked the question with regard to the CME. I mentioned that there's this idea of the polarity, and his comment that it's when the magnetic field is directed south in the CME, that you get the strong coupling into the Earth's magnetic field, and essentially instead of compressing the field, you peel it back and drive strong convection across the polar caps and back into the tail that can then drive strong reconnect or rapid reconnection in the tail and these sorts of injections. So thanks, Jim. That's great.
So does anyone else on the line have questions for John?
I'm sorry, but I got one more then. And that is, so then if, let's just go one step further. We spend a lot of time here talking about auroras, the formation of auroras. So when we're forming auroras and increasing that aurora oval, it's really also being reflected by the Van Allen belt.
That's right. Essentially the way that the auroral oval expands down to lower latitude, that's essentially the magnetopause being peeled back to lower latitudes and closer radial distances. And it's also reflective of additional energy getting dumped into the whole magnetospheric system. And part of the issue is that, okay, so we know during CMEs or interplanetary shock passages that we're dumping energy into the system, and sometimes it comes out just as auroral emission and stuff that's happening at high latitudes. But other times it's happening much closer into the Earth at these lower latitude field lines, and it's still very unclear, how that partition of energy, what controls the partition of energy. What's the knob that's being turned somewhere in the system that says, this time you're going to get a whopping huge outer belt and you're not going to get very much aurora. Whereas in this case, you're going to get a lot of aurora and you're just not going to get anything in terms of radiation belt increases. And so, it's one of the, what's really cool about RBSP and then also about Themis is that they're sharing this volume in the inner magnetosphere. And so Themis was, like during the Beryl campaign, for example, the Themis satellites were on the day side, and during one of the Beryl precipitation events, they actually were able to see the magnetopause move in by, I think it was 4 or 5 Earth radii in response to a big pressure pulse in the solar wind. And so it was really cool to be able to, basically have all of these observing points. Now, one of the ways that I sort of think about this is it's almost like we're running an inside-out laboratory plasma experiment where, instead of sticking probes into the plasma from the outside, we're sticking the probes into the plasma from the inside out and trying to make enough measurements to really understand what's going on. But anyway, so like you said, sometimes you can see very strong aurora and you'll see a very strong response in terms of enhancements in the radiation belt. Sometimes you see them go away completely, and it's a real mixed bag, and we're still trying to figure out how it works. Does that make sense?
Yes, directly, and it sounds very, very interesting.
Well, as you can tell, I'm excited about it. So,
what my next request is, this seems to be at some of this at a level that we could be using. At least if we get access to some of the data, we could start having high school seniors looking at this data and just, obviously by themselves, trying to make connections on that also.
Mm-hmm. Right. And so, part of NASA has this open data policy. And so at this point, all of the instrument teams on RBSP, as well as on Themis and a variety of other missions, they've got data out there. And there's different ways to access it. There's and maybe I can talk with Nancy and you guys some other time about the tools that are out there. I mean, there are online tools that can be used to sort of bring up plots of data and stack them up the way that I had things stacked up, or the way that Dan Baker had them stacked up in his plot, where you've got particle data and fields data and other stuff, and you can sort of just sort of look for basic correlations between stuff, and sort of ask the question, well, every time that you see one of these kinds of changes, do you see a change in the DST, or stuff like that? And that's I think it's a great idea, and maybe we can sort of talk offline about how to get you guys into that. And usually what we do is we have a variety of science data tools that we use on our computers ourselves that go and get the data, and then we look at it and process it. But I think probably the best place is that we could set you guys up with the CDAW web stuff, and maybe do a training on that somehow.
So
that'd be great.
So John, there are several teachers who are part of this community of practice who were not able to make this call today, but we're recording it and we'll upload it to Wigio so that they can view it if they would like to.
Okay.
And some of them may also be interested in that.
Okay.
So maybe in terms of how to proceed, if you could send me an email with just like a paragraph about that, and then I can post it onto Wigio along with the recording, and then any of the lead teachers who are interested in having a separate meeting about that can contact me, and then I can facilitate that, organize that meeting.
Okay. All right. So yeah, I'll get you the initial contact for that, and then we can talk offline about about how to go forward. So, all right. Great.
Great. Well, thank you very much, John. And if there are questions that come up afterwards, please post them to Wigio. John, I know that you're welcome to join Wigio, and I can tell you a little bit more about that afterwards. But I think that probably for right now, the best way to do it is for me to direct questions to you. Unless you're comfortable having people contact you directly, in which case we can provide your email address. So,
let's do moderated first, just because I'm kind of oversubscribed at the moment.
Sure.
But frankly, it's great sort of talking through this. One of the reasons that I love working with you guys is, there really wasn't this sort of opportunity for me at the high school level, to engage with actual scientific data. And I think it's really cool what's been put together to do this. And I'm really, it's fun to participate in. So.
Great. Thank you. So thank you to John, and welcome to Andy, who I see recently joined us. So on our agenda, we had some time for teacher sharing out, and Laura Orr had originally wanted to share something today, but she had another offer she couldn't refuse, being on the fire watchtower today. So she's going to share with us at a future date. And it looks like we are approaching the end of our time together here. So I might just turn it over to you, Ricky, to do our wrap up. How does that sound?
Well, since it was just John today, there's not much to wrap up on, I don't think. So if there's anything else that we can talk about next meeting, or I think we should probably move to that with the amount of time that we have.
Sure. So to give everyone an update for our next meeting in August, at the virtual retreat last time, we had talked about sending out magnets and compasses to you all, and having Laura Peticolas lead you through the mapping magnetic field lines activity, which I know some of you have done before, but many of you haven't done before. So what we're planning for part of the August call is to send those materials to each of you ahead of time, to mail them out, and then as well as the lesson plan, the curriculum guide that goes along with it, and then she'll lead us through that. So we'll use Zoom, but then it'll be kind of like a virtual workshop where we'll all be doing it together, and she'll be presenting that to us. So in terms of mailing out, the materials, we'll use the mailing address that you provided for the honorarium forms on the honorarium, unless you tell us otherwise. If you have a different mailing address that you would like us to send it to, please, please, you can let me know, and I'll make sure that that gets to the right address. And then I see Jane had the question, how many more meetings will we have? So in terms of these monthly meetings, we have August and September left. We had asked for a commitment through the end of September. And then at that point, we'll be taking a look at whether we have monthly meetings or how to proceed beyond September. And part of that is in September, our evaluator, Allison Walker from Cornerstone Evaluation, will be giving you an evaluation survey for you to give feedback on this complete experience from January through the end of September as lead teachers for the community of practice, including your recommendations for moving forward. So as in August and into September, we're going to start to talk more and more about what the next steps are and how to get more teachers involved, and how leadership may shift, and to what extent you want to continue on as lead teachers. And some of you may want to get more involved, some of you may want to be a little bit less involved. And so that's the kind of thing that we'd like to start having discussions about. So in terms of the dates, Ricky, can you go through the dates for both August and September, and we'll see if we've got any conflicts with them at this point? I think you might still be on mute, Ricky.
And I'm sorry, I had it in my email and my folder shut down.
Okay, no problem. So for the dates that we had set from at the beginning, when we laid out the year, Tuesday, August 20th is the set date for August, and then Tuesday, September 17th is the date set for September at the same time that we've been having these. And I know that this July date we had to move around, and that's why we didn't have as high participation. And I'm just going to put those dates out there now. And if anyone has any conflicts with those dates, please let us know right away so that we can adjust if needed. So if you do have a conflict with those dates, and I will send them out over Wigio as well, Tuesday, August 20th and Tuesday, September 17th. If you have a conflict with those dates, please let me know. And if there's enough people who have conflicts, then we can take a look at alternate dates. And Andy, since you are here, do you want to give us a 2-minute highlight summary of your workshop? I was telling everyone at the beginning that you've been at the Community of Practice workshop this week.
Yeah, so I had an opportunity to join in a retreat with other people that are coordinators for Community of Practice groups from all sorts of different places. And they were meeting in Grass Valley, California, and I joined in virtually. So it was a long week, a lot of hard work, but really great stuff. And just working together as a group to look at each other's projects and offer support and ideas in how they can grow and flourish. So you guys got talked about a lot. It was awesome.
Great, thank you. All right, so we're at the end of our hour and a half here. So I'd like to thank you all for joining in today. And also, for those of you who are going to be listening into the recording afterwards, thank you for making it through. And if anyone has any questions or comments, please let us know, and continue to use Wigio to share with each other. And if the last time we didn't use a post-teleconference poll, but we may decide to do that again this time. So we'll let you know about that. And otherwise, I hope everybody has a great weekend.
Thank you.
Have a good one.
Bye-bye.
Bye.
Bye, everybody.
Bye.
Bye. This is Nancy from Texas. Bye, guys. I will see you next time.
Thanks, Nancy, for joining us on the phone.
No problem at all, none whatsoever.
I'd like to take this time to thank the presenter, because this is the kind of information that I would have been feeling that our community of practice is and will really draw other professionals and teachers who are interested in the science. So thank you very much for your time.
Great. Thanks for that comment, Vic.